Hello everybody. Today we will discuss about more basic gates. So far we have seen three basic gates or basic operations in the Boolean logic. One is AND gate, OR gate, and an inverter or a NOT gate. So today we will see that what are the other basic gates which are also considered basic or primitive gates. So using these primitive or basic gates, we construct all the building blocks or bigger digital logic. So the number of gates can be enumerized as like AND OR gate, and there is also XOR gate or exclusive OR gate. Along with that, the three more combination which are inverter of these gates is called NAND gate, NOR gate, and exclusive NOR gate. So these are the gates, these six gates: AND gate, OR gate, XOR gate, NAND, NOR, and XNOR. So these six gates are possible with two or more inputs. Gates which are possible with a single input is inverter or a NOT gate. Along with the inverter or NOT gate, there is also one more gate which is popularly used in some particular cases, is called buffer. So buffer does not do any logic, so whatever is the input, that is given as the output. So it is just sometime it is required to increase the strength of the signal. So we will not discuss this buffer gate here. So what are the new gates we have discussed, we will be discussing today? So one of them is XOR gate. XOR is also called exclusive OR gate. So basic idea here is, let's say there are two inputs. If only one of the input is 1, then the output is 1. So this is the basic behavior or basic functionality of an XOR gate. So if I want to write the truth table for this, that means that only one of the input should be 1, then only output is 1. So I can write it like when both the inputs are 0, the output is 0. When one of the input, means B is 1, A is 0, then output is 1, or A is 1, B is 0, then output is 1. If both A and B are 1, then this would be again 0. So this is the basic behavior of XOR gate, and the symbol for this gate is like you have a OR, and along with the OR there is one more line which is parallel to OR. This signifies the symbol of XOR gate. So whenever we are writing this XOR, we would write it like this. Algebraic symbol is that we write a plus and a circle over plus. That symbol is in algebra whenever we are writing, so that symbol we are using. So along with plus there would be a circle over it. Okay, so this is how we defined XOR gate. And if I want to have a XOR gate which has more than two inputs, then the behavior or the functionality of a XOR gate can be defined as the number of input should be odd. So a number of ones in the input should be odd. So let's say if there are three inputs, A, B, and C, if total number of ones in any input pattern is either 1 or 3, then the output is 1. Otherwise output would be 0. So this is how we define XOR gate. Now let's see the other one, XNOR or exclusive NOR gate. So in exclusive NOR gate, it is effectively if the output of XOR gate is inverted, that would essentially mean XNOR gate. So in a mathematical terms, or in a naive English language, we can say that the output is only 1 if neither of the input is 1 or both the inputs are 1. So the truth table would go like this. So that means when both the inputs are 0, then output is 1. If both the inputs are 1, then also output is 1. Otherwise the output is 0. So you can see the behavior or functionality or truth table, output is exactly inverted of the XOR gate output. So that's why the symbol of the XNOR gate is also very similar to XOR gate, but an inverter associated with the output. So you remember that whenever we have this small circle at the output or at the input, this represents the inverter or NOT gate functionality. So the essentially NOR gate is the XOR gate, XNOR gate is the XOR gate plus an inverter in the output would be XNOR gate. So how can I define it generically? So let's say if the XNOR gate will have more than two inputs, then the output of XNOR gate would be 1 only if the number of inputs is number of ones in the input is even. 0 is also considered even here. So let's say this also include, if this generic definition also include two input XNOR gate. So if the number of ones in any input pattern is 0, 2, 4, 6, then the output of XNOR gate would be 1. So that means at any point of time, if the number of inputs, number of ones in the input is even, then the output is 1. Otherwise, output is 0. Okay, so these were the two new gates which we have introduced. The other gates are NAND gate. NAND gate means a NAND would be followed by the output of an AND gate. So let's say A and B are the two input variables, they are ANDed. If their output is inverted, then that would mean a NAND gate. So that means the truth table would be whatever is the truth table of AND gate, then inverting of that, or basically wherever 0 is there, it would be replaced by 1. That would be the output of a NAND gate. So in a typical AND gate, the output truth table is 0, 0, 0, 1, and so the truth table of NAND gate would be 0 NAND 0 is 1, 0 1, 0 NAND 1 is 1, 1 NAND 0 is again 1, and NAND of 1 and 1 is 0. The symbol would be used very similar to AND gate, but at the output of AND gate, this small circle is there, and circle signifies the inverted output. So whatever is the output of my AND gate would be inverted, that means my NAND gate. So if the input of NAND gates are more than 2, then also we can generically define. So essentially when all the inputs are 1, then only output is 0, otherwise output is going to be 1. So the behavior is generic. Only in the last row of my truth table would give output is 0. That means all the inputs are 1, then only output is 0, otherwise output is 1 in case of a NAND gate. Another similar gate is NOR gate. So NOR gate functionality is not followed by the output of OR gate. So you can also say it like this that my A plus B represent an OR gate. If the output of both of them is inverted, then it would be considered as NOR gate. Let us see the truth table of NOR gate. Truth table of NOR gate is exactly the opposite of whatever is the output of my OR gate. So in OR gate, whenever 0 and 0 is ORed, the output is 0. Here the output is 1. In all other cases, when any one of the input is 1, then the output used to be 1 in case of OR gate. In the NOR gate, when any of the input is 1, then output is 0. So generically we can say that if the input are more than 2, if the inputs are more than 2, if all the inputs are 0, then the output is 1. Otherwise, if at least one of the input is 1, then the output is 0. The symbol is there is a circle after a regular OR gate. Okay, so this is how these few new gates are like the functionality of these new gates. So why we are studying about these new gates, we'll see that they have certain interesting characteristics, they have some interesting properties, and some certain interesting applications. So let's quickly look at these characteristics and applications. So let us see, my this is my NOR gate, so that means A or B is inverted. That means this represent the functionality of a NOR gate. Now if I apply De Morgan's law, what would happen, that this dash should come inside, like for each variable, plus whatever is the AND, this will become this, whatever is the OR, that will become AND. So this expression applying De Morgan's law will become A dash, means inverted A, and inverted B. So this whole thing I can also write it like this, that this NOR gate is essentially equivalent to an AND gate with both the inputs inverted. So this way, this NAND gate, NOR gate is now related to my AND gate with my input inverted. So similarly, if I see a NAND gate, in a NAND gate A dot B, the output is inverted. Now if I apply De Morgan's law, it becomes A dash plus B dash. So symbolically these two are equivalent, so that means a NAND gate is equivalent to an OR gate with the inverted input. So these NAND and NOR gates now become a bridge between AND and OR gate. So essentially, if I want to convert an AND gate to OR gate, then I can use these bubbles or inverters to convert from AND gate to OR gate or NOR gate. So similarly, OR to NAND also it can be converted. So this is so this also give us some intuition that possibly these AND gates, NAND gates, and NOR gates can also be used to design and AND gate, OR gate, or NOT gate. So that's why these NAND and NOR gates are also called universal gates. What is the meaning of universal? So let's say we have only NAND gate which is there with us. So using a single, or using like only the NAND type gates or NAND gates, we can construct any number of digital logic, whatever digital logic is possible. So all of that can be designed, can be constructed using only NAND gates or only NOR gates. So this looks little confusing. Initially when we started our course, we said that the Boolean algebra would be operated upon by three basic operators, that means OR, AND, and NOT. So now we are saying that only one operator is sufficient, that is NAND. So why it is possible? Because NAND can essentially be used to represent NOT gate as well as OR gate as well as AND gate. Why? Because of the properties which we have discussed in our previous slide. So let us say, first of all, if I tie both the inputs of my NAND gate, then if we see the truth table, it would behave like a NOT gate. Similarly, this is the basic property. Now you see, if you remember, if my AND gate, if both the inputs are tied for the AND gate, it simply x dot x is equal to x. So basically it doesn't carry any meaning if both the inputs are tied. But now, because of this inverter, because of this inverted output, it would act like a inverter or a NOT gate. So now, because I can create an inverter out of my AND gate, so I can create a AND gate also out of a NAND gate. So a NAND gate is essentially a inverted output of my AND gate. So if I put another inverter after it, so it would essentially means to me like a AND gate. So although I would require two NAND gates to represent one AND gate, but it is possible, so we can construct an AND gate out of NAND gates. So like in our previous slide, we have seen a relation between OR and NAND gates. So using the same principle, we can also construct an OR gate out of the NAND gate. So what we have seen, that if we take the inverted inputs, if we make the input inverted for a NAND gate, then it would essentially behave like an OR gate. So very similarly, the similar things would happen in the case of NOR gate. So in NOR gate also, like a plus a is equal to a, so that means this also does not have any value, but because of this inverted output, if I tie both the inputs of my NOR gate, it will also effectively work like a NOT gate. So similarly, if I take two NOR gates and the output of one of the NOR gate is connected to both the inputs of my NOR gate, so that means this would effectively work like an inverter, and two inverters will nullify each other, and the output is effectively like a OR gate. Because of the relation between OR and AND, so I can invert both the inputs of my NOR gate, and effectively it will work like a NAND gate. So this way, these NAND and NOR gates can act like a universal gates and can be used almost to construct any Boolean logic or any digital logic. So does it have any application? So yes, initially when people have figured out that these NAND gates can become like, or can be used like a universal gate, so what they did, they created some sort of a programmable hardware by designing a sea of NAND gates. So sea of NAND gates means they created a chip which has thousands of NAND gates, and because fabrication of chip was always a costly affair and a complicated affair, so once they have fabricated these NAND gates, then they used these NAND gates to construct any sort of design, whatever they wanted to configure. So that's the more like a significance, or why we should see that if we have only one universal gate, how we can use that effectively to create any sort of other logic or other gates. So this is one application. The other thing we can see is that as a we have seen that all the Boolean equations we can write in a standard form, which is sum of product or product of sum. So these sum of product and product of sums can also be implemented using NAND gate or NOR gate respectively. So let's consider this sum of product. So I'm taking an example. Let's say sum of product, let's say f is equal to AB plus AC plus BC. So all of these three are product terms, and we are adding these product terms. So we don't see a NAND feature here, so we don't see a inverted output, etc. So how NAND gate can be utilized? So for that, what we can do is we can take f double dash. So yeah, so this is how it would be otherwise implemented. So you'll have three AND gates where A and B would be the input, and the AB, AC and BC would be the input, and the output of all of them would be given to a OR gate. Then the output we can see as F. So now if I want to use a NAND gate, so what I'll do is I'll do a double F double dash. So that means I'll take the inverter of inverted output of AB plus AC plus BC, and then whatever is the output, I'll take another inverted output. So these two dash like F double dash is equal to F. So that's how these two should be equivalent. Now again, if I apply De Morgan's law, so which means that all the terms should be inverted and plus should be converted into dot. So effectively what I am saying is AB dash means the inverted output of A and B, and inverted output of A and C, inverted output of B and C, and then I'll product all of them, and then we'll take another inverted output, so that would be equivalent to F. So essentially what I'm doing is I am creating all these NAND gates. This is A, B dash, this is A and C, inverted output of A and product of A and C, and inverted output of AND of B and C. Now all of these three things are ANDed, and final output is also inverted, so this is also a NAND gate. So essentially like similar to this, any sum of product expression can be represented as AND NAND implementation, can be implemented using NAND gates. So yes, correct. Here you have only the uninverted inputs. What if the inputs are not uninverted, but there are some inverted inputs also, let's say AB dash or AC dash or A dash B dash. So here what we assume that the inputs literals, so as our previous definition goes, the cost of we assume that the input literals are always available in both original form as well as the inverted form. So given this assumption, given this simplification, then we will always assume that, let's say, A dash is also available, B dash is also available, so they can all be connected to our NAND gates, and the output, that means, can be we can see them as F dash. F. Another way of looking at it is, let's say if I put two inverters or two inverters in each of this intermediate output. So if I put two inverters in this intermediate output, then let's see how does it look like. So let's say I have these two inverters for this wire, these two inverters for this wire, these two inverters for this wire. So each of the wire has two inverters. So effectively two inverters would act like a buffer. So that means my whatever is the input would be the output. However, the functionality changes because of this inverter. This AND become NAND, and all these ANDs become NAND, and because of these inverters here, now this OR gate with the inverted input is essentially equivalent to NAND gate. So this is how we can see this sum of product expression and its implementation using NAND gate. So here also the same logic applies. So the basic idea of implementing all the sum of product expressions using NAND gate is that we can have a generic implementation. So that's the reason that we can go for always sum of the product expressions, so that if we have a configurable chip where we have two arrays of NAND gates, then these two arrays of NAND gates can be utilized to design any kind of a configurable circuit. So we'll discuss about these details, that how that circuit would be designed, etc., would be some time later in some other modules. Similarly, these NOR gates can be used for implementation of product of sum expression. So again, let's take a very similar example. So let's say F is a product of sum expression. There are three sum terms: A plus B, A plus C, and B plus C, and all the three sum terms are in product. So that means they are all ANDed. If we see the regular implementation, the regular implementation goes like this: that you'll have three OR gates, and the output of these three OR gates would be ANDed to get the output F. Now, similar to our NAND gate implementation, so we again double invert this F function, F double dash. So that means whatever this expression is, A plus B, A plus C, B plus C, this whole is inverted, and the output is again inverted. So because of De Morgan's law, this first inverter can be converted into A plus B dash plus, now this product is converted into plus, and is converted into OR. So essentially A plus C dash plus B plus C dash, and whatever is the output will again be inverted. So I can put it like this: a plus b dash is essentially a NOR of a plus b. So the output of OR is inverted, that means this expression. Similarly, a plus c OR is inverted, this expression, and OR of b plus c is inverted, that means this expression. And OR of all these three outputs are again ORed and the output is inverted. So these two implementation are essentially equivalent. The first implementation is using OR gate and AND gate, while the second implementation is using only NOR gates. So similar to NAND gate, this can also be understood like, if we make these wires, if we put two inverters here, then the implementation is similar. So let's say we put these inverters, so this output essentially should not change because of these two inverters, and similarly this output should not change because of two inverters, and this output should not change because of these inverters. So now, because of these inverters, this has become a NOR gate, this is also become a NOR gate, and AND gate with the inverted inputs is called NOR gate. So this is how these NOR gates can be used for effective implementation of product of sum expressions, and NAND gate can be used for effective implementation of product of sum of products. So in summary, in this part of lecture we have seen that few new logic gates we have seen. We have seen XOR gate, we have seen XNOR gate, and we also have seen the functionality of NAND and NOR gates. A few interesting characteristics about NOR and NAND gate, that how they can be converted into sort of AND gate and OR gate, and how they works like a universal gates, and how they can be used for effective implementation of product of sum or sum of product expressions.